grams over centimeter cubic. And what they are asking us is for the tension produced by this cable. So as we know, tension is a force. So if we analyze all our equations, we would know that what we need to take out the tension, that is what the problem is asking us, we're going to use the equation velocity equals to the square root of the force, because tension is equal to a force, over our mu. So we're going to rewrite our equation, that is going to be velocity squared times mu equals to the tension. So this is the last one that we would like to reach. So one of the most important things is that we really need to have everything in the same units. So we have millimeters here, we have meters here, we have grams, centimeters. So everything we're going to pass it to the meters. So this is going to be okay because we have meters over second. The diameter is going to be equal to 1.50, that it's going to be the same as 0.0015 meters, because we divide it by 1000. And to get this one, we're going to obtain that grams over meter cube. We're going to have that the new density of the copper is going to be equal to 8,920 kilograms over meter squared. So now we can work everything with this, statements that we made. So the ones in red. First of all, what we really need to remember is that the value of mu is going to be equal to the mass over the length. But as we don't have actually the mass of the copper wire, we can take it out from the equation of the density of our material, that is going to be density equals mass over volume. So to get this, we're going to obtain that our mass is equal to our density times the volume. And now another important thing, let me write the volume right here so we cannot get a little bit confused. Our volume is going to be equal to the area times the height or the length of the wire. And we're going to take into account an area of a circle, because we're going to have a wire that are telling us that the diameter is going to be the 0.0015 meters, right? This is the diameter. So the radius will be equal to 0.0015 over 2 meters, right? Okay, now we have this, we can take the area of a circle, that, as we remember, area is going to be P times the radius squared. Then we're going to substitute this one right here, having that P times R squared times L is equal to our volume. So now we have this equation. We can resubstitute this one that was substituted first in here, because, well, as we do this, it's going to take into the mass. So let me write with another color. Here we're going to have that our mass is going to be equal to the density of the copper that we already have times the volume of everything, and it's going to be pi times the radius squared times L. So to get our new mu, we're going to obtain mass, which is this, density of the copper times pi times the radius squared times the length over the length. So what are we going to do here? We're going to take out our lengths, because they are going to cross out, because dividing it, one, it's going to be the same. And now we can substitute this one right in our equation to get our tension. So for this part, let me write here that our tension would be equal to the velocity square, which one we do have, that it was the first row that I wrote here at the first time. So it's going to be velocity squared. It's going to be 200 squared. And this will be multiplied by our mu that we already wrote it here. That's going to be the density, that our density was 8,920 kilograms over meter cube. That's important to remember. Times our pi times the radius that we wrote right here. It's going to be 0.0015 over 2, this to the square. So this is going to give us our tension, and if we write it right in the calculator, we're going to obtain that is equal to 630.5 newtons, because it's a force. But as we are working with 3 significant figures, we're going to leave it like the tension is going to be equal to 630 newtons. And this is the solution for the first part of our problem. And we're going to write a coupon. I'm really bad drawing, so I hope the teacher doesn't get mad about it. But it's right here. Or something like that. We are going to have that we have transverse waves that travel with a speed of 20 meters. Let me write like this. The speed is of 20 meters, 3 significant figures, sorry, over second. And that this string under a tension is working under a tension of 6 newtons. So and also the problem tells us that what will be the tension required, the tension 2, what will be this one, when we change the speed to 30 meters over second. So how can we relate these numbers so we can get the new tension? As we remember, our equation that's going to work when we have forces, it's going to be equal to the velocity. It's equal to the square root of our force over mu, right? So here we know that we have our velocity for the 2 parts, and we have one tension, but we want to find the other tension. So what are we going to do? For the 2 parts, we're going to take the mu out so we can equal both equations to obtain the second tension that the problem is asking us. So let's take out mu so we can work with it. It's going to be velocity squared is equal to the tension, that is our force, over mu. But we want to take the mu out so we can equal to both equations to get the velocity, the tension. And we're going to obtain that mu, it's going to be equal the tension over the velocity squared. Okay, so this is how it's going to work. Now, what we're going to do is to substitute these variables for the things we want to know. So for the first one, we know that our first velocity will be equal to 20 meters over second, and it's working with a tension of 6 newtons. So our mu1 is equal to our mu2. And now we write that 6 newtons over our velocity squared, that's going to be 20 times rho squared. It's going to be our second tension, that is the one we want to know. Let me write it with another color. Tension 2 over the new velocity that the problem is giving us to the square. That is 30 meters over second to the square. So now we're going to take out our tension squared, that it's going to be the same as our second tension. It's going to be equal to 6, that it's the force of the first one, the tension of the first one, times 30 squared over 20 squared. And for our new tension, if we write it right in the calculator, we're going to obtain that 6 times 30 squared over 20 squared is going to be equal to 13.5 newtons, which will be equal to the tension 2 that the problem is asking us. So this is the easiest way to solve. For the third problem of this week, we're going to have, what it's telling us a problem is that we have a sinusoidal wave traveling to the left, and it has an amplitude of 20 centimeters. Okay, we have an amplitude of 20 centimeters, and our wavelength is going to be equal to 35 centimeters also, and a frequency equal to 12 hertz. Okay, so the transverse position of an element of the medium at t equals 0 and x equals 0 will be equal to the position in y, which is going to be minus 3.0 centimeters. Okay, so they are asking us, well, in this part also, they are telling us that the velocity, it's positive in this part. Okay, now what they are asking us first is to develop the sketch when the position it's in t equals 0, the sketch for the whole wave, and afterwards for our second part we are going to be asked to take out the angular wave number, period angular frequency, and wave speed of the wave. And for this third part they are asking us to write the function or the expression for the entire wave. So let's develop this in two parts. And for our first part, we know that we have a wave moving to the left. That said the problem. And this is for the velocity, for the time, it's equal to 0. So as we also know that we have a sinusoidal wave, but it's important to remember it's the sinusoid, the sine diagram would be like this, okay? So our graph will be like this one. Okay, so first of all, let me take out this so we don't get confused. Let me write our Cartesian plane. It's going to be like here. And what are we really going to graph? It's going to be our distance in y, that it's going to be when it's minus 3 centimeters. So this will be in centimeters, and our position next with our centimeters, right? So what we know is that the amplitude, we can remember that the amplitude is when we have this wave, our amplitude will be this part from the crest up to the our axis here in x. So it's telling us that it's going to be of 20 centimeters. So we know that our wave will do this, right? And so we need 20 centimeters here and 20 centimeters here, right? Let's write our 20 centimeters here and minus 20 centimeters here, okay? Then they are telling us that our wavelength is what is the measure of our complete wave in the horizontal line. So it's of 35 centimeters. So to make a really good scale, what we're going to do is to divide our plane into divisions of 10, right? So our wavelength would be here 10, 20, 30. Let me make it a little bit larger so we can write the 40, so it could pass up to the 35, 40. Okay, and here we're going to write minus 10, minus 20, minus 30. Okay, so let me write here, it's going to be the 35, which is going to cross our wavelength. And what we know is that it's at a minus 3 centimeters position when the time is equal to 0 and the x is equal to 0. So time equal to 0, x equal to 0, but our y is equal to minus 3, right? Let's write it like that. So now we're going to graph our wave. As we know, sinusoidal, I wrote it earlier. We're going to have passing right here, and we're going to have okay, well, I'm not that good drawing, but imagine that it's going to be 20 and 20, right? So this is going to be a part of our graph. Let's write as this part. And like this. Okay, so after this, what it's also important to remember is now here it's our point, which is telling us that it's having a positive velocity, so it's going to be upwards in y, our velocity in y, and to the left for our x. So that is going to be like the position and how is it moving, that particle. And then another important thing for sketching graphs is to write the values of the, well, of all our graph. And now with the wavelength, it's going to be equal to 35 centimeters. But it's up to here, right? So this is our wavelength. Now this part, that's going to be the 20 centimeters of the amplitude of our graph. So now that we have the our graphs sketch, we can proceed to the next part of our problem that will determine us. First, they are asking us to look for the angular wave number, and also, well, let's move to the left. So this is the graph. Okay, so let's write the next part. So for the second part of our problem, we are going to have that they are asking us to obtain which will be the angular wave number, which is going to be determined by the letter K, and the period, which is going to be determined by the letter T, the angular frequency, which is going to be substituted by omega, and the speed of the wave. Okay, so for this part, what it's important to remember are the four speed or velocity. Let me change it to velocity. Which are the four important formulas that we can use to really get these values, because they can be obtained by the direct formulas. For example, our angular wave number will be equal to our K, would be equal to our lambda over, our 2 pi over lambda. Okay, and this will be measured by radians over meters. So for our period, we can determine that it's going to be 1 over the frequency, and this will be measured in seconds. And our omega, that it's going to be equal to a value obtained by the 2 pi over 2 pi times our frequency. And this will be the same as radians over seconds. And for our velocity, we can obtain it by writing the equation of lambda times frequency, and this will be measured by meters over seconds. Okay, so the only thing that we need to do for this part is to substitute all our values that we do have. But first of all, it's important to pass everything on to meters. So we have 35 centimeters for our lambda, that is our wavelength, and it's going to be equal to 0.35 meters. So now we can obtain that for the first part, it's equal to 2 pi over 0.35, and this will be equal to 2 pi over 0.35. It's going to be equal to 17.95 radians over meter. But we're going to use only 3 significant figures, that it would be 17.9 radians over meter. So now we can obtain our period by having that period is equal 1 over 12 hertz, that it's equal to our frequency. So this will be equal to 0.083, and this will be measured in the seconds. It's going to be needed, so 0.083 seconds, right? And now we're going to pass all over again into our omega, our angular velocity, that is going to be 2 pi times our frequency, times 12, and we will obtain that 12 times 2 pi would be the same if 75.39, and it's going to be into radians over second. For significant figures, 75.4 radians over seconds. And now we can obtain our velocity, which will be developed by the wavelength. It's going to be 0.35 times the frequency, that is going to be 12. So 0.35 times 12 would be the same as 4.2 meters over second. Okay, so we have now our values that the problem is asking us, right? This is for the second part of our problem. Now let me erase this to pass to the third part, which is pretty much important because we're going to find the equation that's going to make us determine the function of our wave. So it's important. Okay, so for the last part of our problem, what they are asking us is which will be the function, the expression for the wave function, that it's going to be y times x comma t. So for this one, what we really need to remember is when we have this kind of expression, this will be equal to the amplitude times the sine of our angular wave number, that's represented by k, times the x minus the angular frequency times the time plus our phase constant. And after this, we know that we have our amplitude, we have the angular wave number and our angular frequency. The only one that we're missing is our phase angle, right? So as we want to work everything in the same measurements or units, we're going to pass the amplitude, that is the one right here, 2 meters, so it's going to be as 0.2 meters, and the y, that is going to be the one that we're going to substitute right here, this will be equal to 0.03 meters, right? Now we're going to know that when we have our y equal to 0.03 meters, the x and the time will be equal to 0. So we know that our y 0.03 would be equal to the amplitude, that is going to be 0.2 times the sine of our angular wave number multiplied by the x, that it's going to be 0. So we know that every number or constant multiplied by 0 would be the same as 0. So this will be 0. And as the time is also 0, this answer will be 0. And the only thing that will remain with is with the phase angle. So it's going to be the sine of the phase angle. That is the one that we'd like to know, so we can solve the whole equation. So this will be the same as the sine to the minus 1 times 0.03 over 0.2. This will be the same as the phase angle. And for this result, we're going to obtain that it's going to be 0.150. Okay, but as we're working with 3 significant figures, we're going to let this as 0.151. Okay, now we can substitute everything into our new equation. So we're going to obtain that the positioning y at any time and any position x will be the same as our amplitude, that is going to be 0.2, okay, times the sine of our angular weight number, which we took it in the last part of our problem, and we got that it was 40 over 7 pi, times the x minus the angular frequency. We got it in the last part of the problem, that it was 24 pi times the time plus 0.151. And this will be the solution for the last part of our problem. So we're going to write a cuckoo girl because they are really cool. I'll do my best again. So it's not too bad. But here is she.